Okay, so enthalpy. In order to talk about enthalpy properly, even though we already discussed it to some extent in the last lecture, we need to look once again at the first law of thermodynamics. Now, we've done some calculations, we've looked at some examples, specific conditions, but the idea is that du still equals dq plus dw, and dw is simply negative pdv. But the problem is this: as far as work and heat go, when you calculate them or measure them, depending how you measure them, can actually yield a different value for both of these components. That means that work is path dependent and so is heat. Now this, even though it has some important aspects that can be um, exploited to, perform work simply by using heat and like kind of engines. You could use engines to perform some type of work. The problem is that when you're talking about reactions, if you're dealing with heats that actually can change depending on the conditions, then that means that a person who's doing an experiment on a lab at sea level is going to have results that will differ completely from someone who's doing the experiment at a higher altitude or in a different part of the country. So this kind of presents a big problem. Now, the internal energy, since it's constant, that doesn't really change, and it is path independent entirely. So what we're going to try to do with a little bit of differential equations is to come up with a representation of heat in a way in which it doesn't depend on path. Alright, so the way we do that is by subtracting the work from both sides of the equation. So now we have du plus pdv equating to the heat. Now when this happens, you're basically coupling the work with internal energy, but this whole thing is still constant. So now the heat itself will be independent of path. It may seem kind of silly that that subtraction alone can make such a change, but it turns out to be the case because the internal energy is still constant. So subtracting the value of the work from the constant is going to yield yet another constant itself, which makes this whole thing path independent. Now, what I'm going to do is just to show you how the enthalpy gets derived from the first law of thermodynamics. Specifically, we're going to show that the heat is equal to the enthalpy under one very specific condition. Now, before I get to that though, what I need to highlight here is that what we have on the left side of the equation is internal energy, pressure, and volume. These are all variables that can be measured, or at least determined via the equations. All right, now, from the point of view of differential equations, d, which is the change, when having a collection of constants, or rather variables, in this case u plus pv, technically speaking, what you want to do is distribute the change to all of these variables. You want to change the internal energy, you want to change the pressure, and you want to change the volume. And using rules of differential equations, this is actually not that different than the rules of multiplication. You will multiply the change onto each one of the variables. So you'll have d times u or du. You will have d times p or dp times v. Okay, so now you're applying the change to pressure and pressure only. But then, this is the one thing in which differential equations differs a little bit. The multiplication is not associative, so you actually have to distribute the change also to v separately and exclude p. So now you're going to have this term which is p times change in volume, and before that you got volume times change in pressure, simply by distributing the change into each one of the variables. This is something that you'll see in differential equations if you ever go into high enough math. Now the problem right here is that the format that we have right here, du plus VdP plus PdV is not the same thing as the first law of thermodynamics, which is du equals, du plus PdV equals dq. So what we want to do is get rid of the term VdP. And the best way to do it is to keep the pressure constant, because this second term depends on pressure changing. But if you keep the pressure constant, the change in pressure it's automatically zero, so VdP completely vanishes from the equation, and all of a sudden you end up with the direct differential equation description of the variables u plus PV being equal to exactly the first law of thermodynamics. So du plus PV is now equals dq so long as the pressure is constant. And this particular path, which is independent, right, doesn't matter how you do the actual experiment, as long as you start at the same initial state and end at the same final state, you're guaranteed to have the same result. This is what we call the enthalpy. So the change in u plus PV is technically the change in enthalpy. This is the actual rigorous definition of enthalpy itself. But the gist of it is that the changing enthalpy is the same thing as the changing heat of a reaction, as long as this is done at constant pressure. And you can ensure this to be the case simply by performing a reaction in an open flask. That's all it takes. But the beauty of it is that the enthalpy, which is the heat of the reaction, now doesn't depend on the path, right? The heat or enthalpy is path independent. Start at the same initial point and at the same final point, you're guaranteed to have the same result every single time. And if you want to be exact about this, the enthalpy and the heat, which are now path independent, are said to be state functions. And state functions, when you think about a multivariable function, simply stated, what it says is that if you look at the rate of change along one of the parameters, it could be the parameter going left and right, followed by the rate of change in the parameter going in and out, that has to equal the rate of change of the function going in and out, followed by the rate of change going sideways. And the idea right here is that if you change how you look at the rate of change, that shouldn't affect the result whatsoever if these functions are to be path independent or to be state functions. Now this setup right here is what we call the Maxwell relationship of multivariable functions. This is something you're not going to be tested on in this class, but I want you to be aware of it. By the time you get to physics, by the time you get into higher math, this is where all of the applications actually start, lining up in terms of higher math. All right, now we're probably going to stop right here and continue talking about the enthalpy of formation in the next video.